What's going on, you guys? Mr. Allen here talking some symmetry of different polygons in this video. So we can have horizontal symmetry like this, which will usually notate with a vertical line through it, right? Because it's going to fold over that vertical line. That's horizontal symmetry. We could have vertical symmetry, top to bottom, right? Which we would divide it with a horizontal line. You can have rotational symmetry if you're rotating it, say, 90 degrees, or even something like 60 or 30 or 45, whatever, okay? So let's get after this thing. And you can have more than one type of symmetry, okay? So I've got congruent marks on a lot of these things because I wasn't necessarily drawing them perfect, but it looks like we have an isosceles triangle here. So I know that this is going to fold over that line right there. So that's going to be vertical symmetry, okay? So vertical symmetry. All right. Next one over here, we got a trapezoid, an isosceles trapezoid. I got the two parallel bases, got the congruent sides there. So I can have myself, some horizontal symmetry, right? So horizontal symmetry. Beautiful. Any other kind of symmetry there? Could I rotate it? No, then it would be like upside down, right? It'd be like this, like that. So not going to work, right? So horizontal symmetry for that one. Okay. Looks like we got a rectangle here, right? I got opposite sides congruent, got a right angle, which means that all of them are going to end up being right angles based on properties of quadrilaterals. So for this one, we could say, well, I've got horizontal symmetry. I've got vertical symmetry, right? I even would have like 180 degree rotational symmetry. So I'll write that down. Vertical symmetry, horizontal symmetry, and rotation. Rotation 180 degrees. Nice. What about 270 or 90? No, because these are different lengths, so that would be different. A square, you'd get that. But only for a rectangle here, it's only going to be rotational for 180 degrees. And one thing to note about that, if I were to say like on a graph, okay, if I were to reflect over my y-axis and then over my x-axis, that is equivalent to a rotation of 180 degrees in either direction. So sometimes we'll ask that kind of question on a test, like what's the equivalent to reflecting over the x-axis and y-axis, or doing a horizontal and a vertical reflection? It would be a rotation of 180 degrees. Nice. All right, this next triangle here, it almost looks like isosceles, but there's no markings here, so more scalene. Yes, okay. So I don't have any none. Yay. Okay, there we go. No symmetry in that one, right? No sides are congruent, no angles are congruent as marked, right? So, nope. All right, octagon, bro. Looks like a regular polygon. I got all the sides there marked. It is a regular octagon. So we got horizontal symmetry, right? We could fold it over this way. I could even, fold it vertical. I could have vertical symmetry here. I could also have some, we could really draw all these different lines in here, right? Boom, it's going to be symmetric there, here. I think I got them all. Yeah, okay. So really I can bisect two of these sides. Is going to go through the center of this thing, because a regular polygon can actually be inscribed in a circle, so it has a center to it if it's a regular polygon. So I've got a lot of symmetry going on here, okay? I'm not even going to write them all down. But another thing I want to write down, though, is the rotational symmetry. Okay, so we got horizontal. Horizontal, vertical. We got rotational. And rotation for this one is actually, we're going to take 360, and divide it by the number of sides or angles. That's going to give me 45. There we go. Degrees. So I have rotation of 45 degrees. Every 45 degrees I turn this thing, it'll be the same shape. Right, so that's rotational symmetry. Okay. Pentagon. Same kind of sort of thing going on here. I'm going to have horizontal symmetry. I can fold it over right now, how it's drawn. But I'm also going to have, so we'll write that down, horizontal symmetry. I'm also going to have some other lines of symmetry here that aren't necessarily one particular direction, right? It's going to be going here through this vertex. It's going to go through this vertex in the middle of the opposite side. It's going to go through this vertex and the middle of the opposite side. And got one more. This vertex in the middle of the opposite side. And they'd all meet in the center if this was drawn perfectly, right? All meet through the center of that regular polygon, that regular pentagon, because regular polygons can be inscribed in a circle. Okay, so it's got a center. Well, when we have all these lines of symmetry, just like we had here, okay, and all those sides are congruent, we likely have rotational symmetry. So what is 360 divided by 5 sides? Well, that's going to be 72 degrees. So let me write that over here. Rotational by 72 degrees. There we go. So if it was a hexagon, I'd take 360 divided by 6. That's going to give me 60 degrees, right? You can do that for really any regular polygon. It's going to have rotational symmetry to it because every time you turn it the certain amount of degrees, it's going to line back up and be the same exact polygon. All right, these are all isometries here, guys. So I'm not changing size, right, or shape when I do any kind of a reflection the other way, a rotation, right? So those are all examples of isometries, not where you're going to do a dilation. Dilation is going to change size or, things like that. So that's not, right? But it's only if it's rigid. If it doesn't change size, then it's an isometry. Okay. Beautiful. Wonderful. All right. That's awesome, guys. Symmetry is dope. You guys are dope. Have a wonderful day, and thanks for watching. Peace out.